So as we were discussing last day, bidentate ligands. Now we are going to discuss tridentate ligands. That means there are three donor points. Okay. Now, as you can see, this is called 2,6 pyridine dicarboxylate. This is one donor point. That is one donor point, and that is the another donor point. Okay. Similarly, terpyridine is just the higher homologue of 2,2-bipyridine. So this was your 2,2-bipyridine. Now you think in the sixth position of the pyridine you have joined another pyridine molecule like that. So now you have three donor points like this one, that one, and that one. So this is called terpy. In your abbreviation, you will write as terpy. Let's go ahead and do tetradentate ligands. That means there are now four such donor points. Okay, so one of it is, just have a look. We can have something like that, like that. And as you can see over here, there are four such donor points like this, like that, and like that. So this is going to be a tetradentate ligand. This is basically silane. Okay, and over here you can see there are, so this is silane H2. Okay, if you remove this H from here, if you remove the H from here, that is, suppose I remove this H from here and I make this as negative charge. Alright, I make this as negative, this as negative, so this is a di-negative, and here this is another donor point and that is another donor point. In case of this one, this is called a porphyrin. Okay, a structure very similar to this is present in your blood, which is known as protoporphyrin. Okay, so your blood contains hemoglobin, and that hemoglobin is having, if you remove the iron from it, then the ligand that is making the hemoglobin will be having a structure something like that. Okay, so this is a very important ligand, and it is also, so basically where is your iron connected? Your iron is connected over here, something like that. Okay, and there is another protein part which is called globin. So that is not much importance for us at this level of yours. Just need to know that your porphyrin is going to be a tetradentate ligand, and when it is hemoglobin or heme, so inside a heme we have one iron. Okay. Apart from that, people may ask you whether this system is aromatic. So you will say yes, this is an aromatic system. And sometimes they might ask you what is the number of pi electrons. So you just follow this peripheral boundary, which is marked in blue. That means like that. Okay. So how many electrons do you see over here? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. That means this is a 18 pi electron system. All right. And 18 is obviously a Huckel rule, Huckel number. So if you calculate 4n plus 2 equal to 18, all right, then what is the value of n that you get? It will be 4. All right. So this ligand has some importance. What is the importance? In blood, the protoporphyrin has a very similar structure to porphyrin. Hold on. Did I do something wrong? Okay. Yeah. So in blood, your protoporphyrin has a very similar structure to porphyrin, and it has iron 2 in it. So sometimes they might ask you what ligand system is present in blood and what is the metal inside it. Similarly, the chlorophyll, which is the green pigment in plant, okay, there are actually 5 types of chlorophyll, so we need not to study all that. Okay, so chlorophyll also are very much similar. Okay, it also is very much similar to this porphyrin ring. There also inside this core. Okay, this core. Which core am I talking about? This core. Okay, there we have magnesium 2 present. So this type of questions can be asked to you, especially for students who are appearing for the exam Neet, because it is related to biology, right? So you have to know these things. Next, if I say hexadented ligand, that means we have now to consider 6 donor points, and out here we have something called EDTA 2 minus, or we can say 4 minus. This is known as ethylene diamine tetraacetate. Tetraacetate. What is the structures? Ethylene diamine we already know. There is a nitrogen joined by a 2 carbon chain. So it is saying tetraacetate, that means it will be CH2COOE. CH2COO minus, like that. OO minus. This portion is your ethylene diamine, and these are the tetracetate part. Now you can see there are four of it. That's why we are calling it as tetracetate. Okay. Now if you consider donor site, so this is one donor site. All right, let me join. So people are joining so late today. হ্যাঁ তোকে জয়েন করলাম তো। Okay, so sorry. Yeah, let me change the. Huh. So this is one donor point. That is one donor point. This one, that one, that one, and that one. Okay. Now, interesting questions are asked on this. Wait. This girl is not able to join. Okay, so some questions related to or facts related to EDTA. Why 4 minus? As you can see over here, negative, 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 and another negative. Okay, that's why it is 4 minus. Or else the neutral will be what? Basically, H4 EDTA. That is how it is written. Understood? Now, first of all, this ligand it is used to estimate the hardness of water. I will discuss this separately. Okay, using complexometric titration. Okay. So what is done basically over here, that maybe there is say calcium and magnesium inside a solution. Okay, so you use a indicator which is called EBT. Okay, what is the meaning of EBT? Areochrome black tea. And so this EBT will form complexes with either calcium or magnesium. EBT, when it is free, this is blue in color. Okay, but when EBT is forming a complex with calcium or magnesium, it is basically wine red in color. So the moment you add the EDTA solution, okay, maintaining the pH to be at around say 9.5, all right. So EDTA will start complexing with calcium, forming calcium EDTA complex, or say the magnesium EDTA complex. That means what? It is slowly going to start releasing the EBT. So what will happen? The solution from wine red color will go to, if these ones are colorless, the color of the solution from wine red will again change to what? Blue. And that is how you understand that the reaction is completed, or we have reached the end point. So we have found out a method by which we can estimate the concentration of calcium or magnesium inside the solution. Okay. And obviously this is reported in ppm level, that is in parts per million. Okay, which is basically what the formula is. Please understand, mass, okay, of say A by total mass into 10 to the power 6, or we can say this to be as mass fraction into 10 to the power 6. Now, what is the mathematical meaning of ppm? It means 100. If I say 100 ppm, okay, then what does it mean? It means 100 gram is of solute, say, of solute is present in 1000, not 1000, I will say rather 100,000 gram of solution. Okay, that is what it means. So this is one way one can measure using complexometric titration the hardness of water. Besides that, we can measure another extension of this thing is we can measure the concentration of calcium inside milk. Okay, milk contains calcium lactate, so we can measure the amount of calcium that is present inside the milk. Okay, also during blood test or blood collection, stop the coagulation of blood. Okay, coagulation मतलब क्या? To stop the blood to thicken. Of blood. Okay, an anticoagulant is added. Coagulation happens because of interaction of air with blood in presence of calcium that is already present inside the blood plasma. Okay, and the anticoagulant is what over here? It is EDTA. So the EDTA's job over here is to take up the calcium, okay, hold on to it to stop this coagulation taking place inside blood. All right. So there are three practical uses of this ligand EDTA. As I have mentioned, one is to measure the concentration of calcium inside milk or concentration of calcium inside the water to measure the hardness of water, or we can say that it can also be used as an anticoagulant so that the coagulation of the blood can be stopped. Now, another new terminology which is known as flexidented ligands. Now, what is the meaning of flexidented ligands? So, as it is, you can see there is the word flexi means flexibility. So, here basically there is a ligand that has say multiple donor sites, but it is only using, say it has 5 donor sites, but it is selectively using 4, or maybe using 3, or maybe using 2 donor sites. So it is showing some flexibility while it is binding with a metal ion. Okay, it is selectively using 3 or 4 or 2, but it has 5 such donor sites. Okay, so such flexibility that it is showing, it is known as the flexidented ligand. So a ligand that has variable denticity, that is the binding ability, are called flexidented ligands. So sometimes it can be seen that your EDTA, which is having 6 donor sites, okay, it can function only using 5 or 4 such donor sites. Okay, even some ligands, okay, we have discussed before, such as say CO3 2 minus. Okay, so it can function as a monodentate, maybe also bidentate, or it can also function as tridentate. So this type of flexibility that it is showing, we will call this as a flexidentate ligand. Even the acetate can be mono or bidentate. Okay, the nitrate can also be functioning as mono, bi, and tridentate ligands. Okay, so some examples over here just to make you understand that this kind of ligands can show such flexibility. Now, another terminology, ambiented ligands. What are ambiented ligands? The ambiented word comes from ambidextrous. That means a person whose both the hand and the left hand they work equally. Okay, so ambiented word comes from ambidextrous. Okay, ambidextrous means a person who can use both the right hand and the left hand equally. Somebody like Saurav Ganguly, right? He can bat with left hand or also with the right hand. Bowls with the right hand and bats with the left hand. Somebody like that. Even Sachin can bat equally, with the left hand and the right hand. So these people are ambidextrous in that sense. Okay. Even the warrior in Mahabharata, okay, Arjun, he could use both the hands equally, so he was ambidextrous. Now here, in terms of ligands, we will say these are ligands having two different, okay, not similar but different donor sites, but selectively uses one. Okay, selectively uses one. So suppose you have a nitro group and there is electron pair in the nitrogen, so it can come from the nitrogen. There is also electron pair on the oxygen, so even the oxygen can give its electron. So this type of ligand, we will say it is ambiented ligand. Even we can have something like SCN where the lone pair is also on the nitrogen and also on the S. So coordination can happen from S or from the end. Okay. Similarly, we have OCN. So this is called cyanate. This is called thiocyanate. So coordination can happen from O or it can happen from N. All right, something like that. Another interesting ligand you can see over here, we have C double bond S, and we have O. Okay. Now another resonating form over here, or I would say another way it can exist. It can exist like this. Okay. So coordination can happen from O when the minus charge is on the O, or coordination can happen from the S when the charge is on the S. So this type of ligands we will be calling them as ambiented ligands. Okay. Now this kind of ambiented ligands, when they are present, I'm giving you a hint from beforehand, they will cause because ligation is changing, so ligand isomerism. So if you are given a complex and they are asking this is containing ambiented ligand, what kind of isomerism it will show, you will say ligand isomerism. As simple as that. So now, having discussed things relating to types of ligands, flexidented and ambiented behavior, all right. So, and in the flexidented ligand, we have already discussed, you know, that complexes or the ligand can be showing flexibility while using the donor atoms, that it can use two donor atoms or three donor atoms. Suppose there are six donor atoms, you can use only two or three or four or five. This kind of flexibility is called flexidented ligand behavior. All right. So having done all that, what we are going to do right now is we're going to talk about what are chelating ligands. Okay. What are chelating ligands? Simply, ligands that form closed rings on coordination to the metal are called chelating ligands. Okay. Mostly this type of behavior will be shown by polydented ligands. So your monodented ligands will not be showing any chelating behavior. That should be kept in mind. All right. And over here, mostly five or six membered rings are formed, which are strain free. That means there is less angle strain than four or seven membered rings. Okay. So let's take one example. Suppose we have been given this ethylene diamine, all right, and we have one metal. Let's keep it general. Let's call it as Mn plus. So here there is two such donor sites. So one donation from here and another donation from here. Now when you join this part, please have a close look. It is forming what? A cycle or a ring, and you can call this as a 5-member tree, just like that. So what will be asked to you in a examination hall? Suppose I give you a question like this. How many rings are formed by let's say EDTA, all right, EDTA 4 minus on complexation with calcium 2 plus, let's say. So what we will do, just have a look. We have this EDTA. So first of all, we will write the N like this. We place the calcium over here and you join. So this is your first ring, okay? Now, it is having this tetraacetate ligand. So this is another ring. So this is ring number 2. Keep an eye. Now, again one more continuation. So this is ring number 3. So there are tetraacetate. Right now I am only attached. I have only attached 2 such acetate functionalities. Okay. So another is what? Suppose like this. So one more. So that is 5. Another one like that. Yeah. Let me just make it much more. Yeah. Like that. So now this is another one. So this is 6. So the EDTA ligand, once it complexes with calcium, it is basically making how many such rings? You will say, so 5. So this type of question they can be asking you in an examination hall. Alright. They can also give you something like, say, a salin. Alright, what is a salin? Again, your salin is something like that. Okay. Something like this, okay. And you place one metal over here. Say it is now Mn. Okay. Now if you join ring number 1, over here you join ring number 2, here you join, this is ring number 3, and this will be having one more chlorine on the top. So basically salin on coordination with the Mn, okay, it is forming 3 such rings. Okay. So this is basically, we will say, coordination of salin with Mn. Yeah, I just missed the hydrogens. Let me write the hydrogens over here. Oh no, okay, it's okay. So this is coordination of Salin with Mn3. Okay, how many rings? How many chelate rings? Or 5-membered rings are formed over here. Alright, so that is what it is. Now, let's go to the next part, which is related to isomerism. So this is something new for you now. We have studied isomerism in the organic chemistry while we were doing. Now we will be doing isomerism, both geometrical and we will be doing optical in coordination complexes, that is in inorganic chemistry. Okay, so for that, what we will do is we will begin with the structural isomerism and then slowly we will move into the stereoisomerism part, which will be including your geometrical isomerism and optical isomerism. Okay, and we will do a lot of variations over there. So first of all, let's make a broad heading in which we are saying, at least for this section, that is in coordination chemistry, types of isomerism. Okay, so in types of isomerism, when it comes to structural isomerism, we will be calling of the ionization, sorry, ionization isomerism. Okay, now what is the meaning of ionization isomerism? In simple language, when there is exchange of ions or groups between the complexes, between the complex ions secondary and ionization sphere. Okay, then we will call it as ionization isomerism. So what is the meaning of it in simple language? Suppose we have been given a CO, NH3 whole 5, Br, SO4. Okay, so if this SO4 from outside, which is now in the ionization sphere, goes inside this and the Br comes out. So that means what? CO, NH3 whole 5, SO4 goes inside and Br is outside. So there is basically exchange of ions. Inside this third bracket, we call this as what? Secondary sphere or the coordination sphere in terms of the terminologies given by Warner. Okay, and the outside this third bracket we are calling this as ionization sphere. So whenever the ions interchange their position, okay, do not be bothered about the charge on the ion. Sulfate here may be -2 and Br may be -1. So that is not a big deal. Just the ions are exchanging. Okay, so if there is a Br inside, Br's position is exchanged with sulfate, then we will be calling this as simply as ionization isomerism. So basically, when the coordinating ions or ligands inside the complex and the ions outside the complex, they exchange their position. This type of complexes will be known as ionization isomers. Another example is what? Suppose I give you COCl2 NH3 whole 4 NO2. Okay, and now if you exchange one of the chlorine with the NO2, so you are basically making this, then you have NO2 and then you have NH3 whole 4 and Cl. So these two complexes will be called again as ionization isomers because the ions are exchanging. Okay. Similarly, next one, suppose I have given you PtCl2 NH3 whole 4 Br2, and then you have another one which is PT Br2 is inside, then NH3 whole 4 Cl2. Similarly, both of them will be again called as ionization isomers. Interestingly, suppose you are taking these two complexes. Okay. Now out here, suppose this complex is A and this is complex B. These two complexes will be behaving different chemically when you run some chemical test over it. Suppose you have taken the first complex and you dissolve this in water. Alright. And as we have learned, what will happen? That the unit that is within the third bracket will remain intact. This will be +2 charge because sulfate over here is -2 charge. So this is +2 and we will be having SO4 2 minus. Okay, as simple as that. So now this is equated and that is equated. That means over here Br minus is not free but the sulfate is free. So if you do a test for the sulfate, which is by adding barium chloride solution to this, then what we will get? We will get a precipitate of barium sulfate from here, which is obviously white. Alright. So this particular complex B, oh, no, it is A. The complex A will be giving the test for sulfate. Similarly, if you do B, suppose you have CO NH3 whole 5 SO4 Br added to water, and then you have this complex dissociating inside solution. So basically once it dissociates, now what is outside? It is Br, so this will be having plus charge and Br minus will be released inside the solution. So now if you do a test for sulfate, you will not get the test for sulfate, but if you add AgNO3 drops over here, okay, then you will get a yellow precipitate for AgBr. So what you can say from these two tests, that complex A will be giving the test for the sulfate and complex B will be giving the test for the bromide, but not vice versa. Okay, so that is an important chemical test that you can do for such complexes A and B to identify which particular anion is lying outside the complex. Alright? এটা মাথায় ঢুকেছে? Yes or no বলো? Okay. Next is hydrate isomerism. Now, whenever I say hydrate isomerism, that means it has to do something with water. Okay. What do we say? This isomerism arises out of different disposition, placement of water molecules, that means aqua molecules, inside and outside the first sphere of coordination. Alright. So out here, suppose we take this complex, that is, for example, CrH2O whole 6, alright, this one. So this one, which is violet in color, alright, if you were going to try to remove these water molecules using concentrated H2SO4, your observation will be no water molecule is lost. Okay, over concentrated H2SO4. So this is one type of a drying agent, concentrated H2SO4. It absorbs moisture from the air. So if you keep this complex inside a petri dish, okay, and then you surround it by, don't add it to it, but keep it in an environment where it is surrounded by, say, H2SO4. Okay, maybe it is there in the petri dish like this. Okay, and then outside you have one beaker or another bigger petri dish, okay, in which you have this sulfuric acid like that. Okay, and then you keep it inside, okay, a desiccator or a or a container in which you have removed the air. So what will happen if this water molecule was outside the complex, then these water molecules will be lost. But if it is inside the complex or the secondary sphere of coordination, okay, or we can say directly coordinated to the chromium, then the water molecules will not be lost. Okay, that is the basically physical picture that you have to understand. So what we will say, if the water molecule is inside the complex, that is the secondary coordination sphere, it will not be lost. However, if you were to add AgNO3 to this complex, aqueous, can you tell me how many chlorine ions will be precipitated, or how many molecules of AgCl will be precipitated? This complex, when dissolved in water, how many chlorine ions will be released?
3, sir.
3. So obviously it will be 3 moles of AgCl that will be precipitated. So far that is clear to you. Alright. Next, another complex CrH2O whole 5 Cl Cl2 dot H2O, which is obviously green in color, and if it is again just in a similar manner surrounded by H2SO4, and this complex is kept inside a petri dish. Now, since the water molecule is now lying outside the coordination sphere, what will be your observation? That it will lose 1 mole of H2O. So, if you have taken this to be as 1 mole, then 1 mole of water will be lost from this complex. Okay. Similarly, if you were to add AgNO3, can you tell me how many ions of chlorine will be precipitated out? Outside the coordination sphere, how many chlorine are there?
2.
So you will say 2 AgCl or 2 moles of AgCl will be given out from this complex. Is it clear?
Yes, sir.
Okay. Now, suppose we took another complex which is chlorine H2O whole 4 Cl2, and there is only one chlorine outside. So accordingly there will be what? 2 H2O. So if you keep again over concentrated H2SO4, how many water molecules will be lost? 2 moles
2.
of H2O will be lost. Okay. And if you were to add AgNO3, then how many chlorine will be lost or precipitated
1.
out? 1. Okay. So that is how scientists were able to identify how these complexes, even before knowing the structures, okay, physically viewing the structures, because at those times, there was no X-ray techniques to physically see the structures, okay, of molecules. But by using simple analytical techniques, they were able to, or metathetic reactions, they were able to understand what was the arrangement of the ions inside and outside the coordination sphere for these type of complexes. All right. Now, a few more examples, and you tell me what kind of isomerism it is showing. Suppose you have CrEn whole twice, H2O whole twice, and outside we have Br3. And I give you another one in which I'm saying Cr, Br, En whole twice, H2O, Br2 dot H2O. So what kind of isomerism it is showing? Where is the variation among these two?
Sir, এখানেও 2 moles of H2 will be lost হবে।
No, is this H2 outside? No, it is inside, so it will not be lost. So here in this complex you are seeing two H2O molecules inside, and here you are having one molecule of H2 outside. So there is a variation in the amount of water molecules inside and outside the bracket. So obviously they are showing what? Hydrate isomerism. This is called what? This new isomerism we are called hydrate isomerism. Okay. So again you see another complex which is obviously COCl H2O NH3 whole 4. Okay, and we have Cl2, and we have given another one which is again isomer to this. You just tell me what kind of isomerism it is showing. So these two are differing in what? Where is the difference?
স্যার স্ক্রিনে তো কিছু দেখাচ্ছে না।
হ্যাঁ,
হ্যাঁ স্যার।
এবার দেখাচ্ছে?